Melanie Mitchell is professor at the Santa Fe Institute. Her current research focuses on conceptual abstraction and analogy making in artificial intelligence systems. She is a student of Doug Hofstadter's, among others. Is that correct?
Yeah.
You say very quietly. Melanie is the author or editor of 6 books and numerous scholarly papers in the fields of artificial intelligence, cognitive science, and complex systems. Her 2009 book, Complexity, A Guided Tour, won the 2010 Phi Beta Kappa Science Book Award, and her 2019 book, Artificial Intelligence, A Guide for Thinking Humans, is a finalist for the 2023, or was a finalist for the 2023 Cosmo Prize. Did you win it?
No.
Okay, well, it's still a finalist for that.
Yeah.
And the last thing I want to tell you is that when the clock time for this is over, which is 90 minutes from now, I'm going to read a memorial reminiscences from Doug Hofstadter for 10 minutes. So if you want to hear more about Dan Dennett, stay for 10 minutes after the end of Melanie. Go ahead, please.
Okay, thank you. Thanks to everybody for coming. I'm going to talk about the challenge of understanding the world for humans and AI. So, you know, we've been in the deep learning revolution for a while, and AI has gotten astoundingly better at many things, but do they actually understand the data that they process? This is really the question that I think this entire summer school is looking at. And does it matter? Well, let's look at some failures of understanding in AI systems, particularly AI systems before the generative AI revolution. So this particular paper focused on images that were image categories that were in the ImageNet image recognition challenge. It's like a school bus. This is a neural network that's been trained on ImageNet that can recognize the school bus correctly with 100% confidence. But if the object is transposed or rotated via Photoshop into various poses, it changes the classification dramatically. Now, the network is 99% certain it's a garbage truck, a punching bag, and a snowplow. So this shows a kind of brittleness of whatever understanding the system could be said to have of this object, in that it's not robust to these kinds of changes of pose. And this kind of brittleness is seen in machine learning, in computer vision and language in general. For instance, here, this is a picture of a vision system on a self-driving car that is correctly recognizing cars, but is recognizing these pictures of bicycles and people on an ad on the back of a van for e-bikes. It doesn't sort of distinguish between things that are in ads and things that are in the real world, sort of giving us a lack of understanding of context. This was perhaps shown even more by this example, where a Tesla driver tweeted that when he was using his self-driving car software, his car kept slamming on the brakes in this area with no stop sign. But after a few drives, he noticed this billboard, which you can see blown up here, is an ad with some kind of official holding up a stop sign in the billboard, which the car interpreted as a real stop sign. And I should say, I don't have a slide for it here, but people are now trying to fool robo-taxis in San Francisco by having T-shirts that have stop signs on them, and they stand out in the sidewalk, and this car sometimes will stop in response to the T-shirt. We've seen a lot of examples of shortcuts in machine learning systems. So for example, in this paper, these researchers trained a deep neural network to distinguish malignant and non-malignant skin lesions. But what they found when they looked into it how it was doing this classification, they noticed the algorithm appeared more likely to interpret images with rulers as malignant. Well, okay, so images with malignant lesions typically had rulers because, the pathologist wanted to measure the size of the malignancy. And that's so the neural network learned that convenient shortcut to getting correct classifications without really understanding what the humans were trying to teach it. Google Translate can still make mistakes based on ambiguities in words. So here, if you try to translate this sentence, the legislator accidentally left a copy of the important bill he was writing in the taxi. If I translate that into French, Google Translate translated bill as facture, which is the wrong sense of the word bill. This is more like an invoice than a legislative bill. And in fact, in the real world, people have found that translation software is not robust enough to be trusted. Like if we're going to use it for critical cases like translating asylum requests, it can make errors that can really be harmful to humans. But now we're in a new age of large language models and other generative AI systems. And there's some feeling among people, a lot of people, that they've achieved a richer human-like understanding than previous AI systems. And indeed, I can ask ChatGPT to translate this same sentence into French, and it gets the right translation for bill. And I can ask it why it translated it that way, and it will tell me in a very verbose way, as it tends to do, about why it's translating it that way. And it's clear that the bill refers to a legal document, etc. If the context were different, it would be different. And it does seem to understand the sentences that it's processing. And Terry Sinofsky, who is a neuroscientist and a neural net pioneer, wrote this very interesting paper on large language models in which he said, it was if a space alien suddenly appeared that could communicate with us in an eerily human way. LLMs are not human, but they're superhuman in some aspects. Some aspects of their behavior appear to be intelligent. But if it's not human intelligence, what is the nature of their intelligence? And this is what we're all kind of grappling with. How do we characterize what these systems are, what their intelligence and understanding consist of? Well, some people have made a lot of, optimistic claims about large language models. Blaise Aguirre y Arcus, who's a researcher and executive at Google, wrote that these systems really do understand a wide range of concepts. And I think he would say that understand in a human-like way. But he says its understanding is informed purely by text, but it's real understanding. On the other side of this debate, we get people like Jake Browning and Yann LeCun, who say a system trained on language alone will never approximate human intelligence, even if trained from now until the heat death of the universe. So they are on that other side. They would not attribute human-like understanding or intelligence to these machines. Well, a group of researchers did a survey of the NLP community a couple years ago, and they asked people to agree or disagree. Some generative models trained only on text, given enough data and resources, could understand natural language in some non-trivial sense. And the result was really split along the middle, 50-50 had strong, opinions negatively or positively about that. I don't know what would happen if people were given the same survey today. It would be interesting to try, but people seem to have strong opinions on this. Well, here's someone who claimed that these systems understand in a human-like way. Ilya Sutskever, co-founder of OpenAI, said that when we train a large neural network to accurately predict the next word in lots of texts, it's learning a world model. This text is actually a projection of the world. What the neural network is learning is more and more aspects of the world, of people, of the human conditions, their hopes, dreams, and motivations. The network learns a compressed, abstract, usable representation of that. And to some people, this notion of compressed, abstract, usable representation might be what the definition of understanding is. And I think Susskiver would say definitely these machines are understanding. Well, this notion of world models, he said these systems are learning world models. This notion of world models is a term that's been used, but what does it actually mean? Well, probably the best example of looking at world models in neural networks is the case of Othello, the game of Othello, not the play, Shakespeare play, where these are two different papers that looked at systems that are trained on sequences of text that represent Othello game sequences, and then probed the neural networks for world models. So let me just tell you a little briefly about this. Othello is a game that's played on an 8x8 board, and you have black and white tiles that are placed down. A tile has to be placed. The board starts like this in image A, and a tile has to be placed in a way that captures a piece, that is, surrounds the piece either in some direction with pieces of the opposite color. So here's black moving here, and then the white piece that was captured flips to black. Okay, and then here's another move where white moves here at D3, and the piece in the middle is flipped to white. And so you keep going on until one side or the other. The board is actually, nobody can make a move, and then the person with the most pieces wins. So what these groups did is they took a relatively small transformer, one with 8 transformer block layers, and they fed it sequences of legal moves generated from random games. There were legal moves, but the games were simulated by searching along game tree. And they're tokens like this, E3, D3, C5, that represent board positions. And the classification task or the prediction task was to predict the next legal move in that sequence. So the actual move that was in the simulated sequence, sort of like predicting the next word in a text, the way that ChatGPT might do. Okay, so this system didn't know, it wasn't told that it was playing a game. It wasn't told that there were alternating players. It wasn't told that there was a board or anything like that. All it was given was these tokens, E3, D3, C5. And it learned very well to predict the next sequence in the token. Okay. Now, what did it learn actually? How is it doing this task? Well, the researchers trained a linear probe, a simple linear classifier that input activations from one of these layers, one of these transformer block layers, and then used that trained it to predict the contents of each board position. So basically, the way that they did it, it's a little bit complicated to explain, but they took this linear classifier, which input the transformer activations after a set of tokens were input, and it trained this thing to predict for each board position, each of the 64 board positions, whether the position was filled with, if it was black's move, whether it was filled with a black tile, or if it's white's move, whether it was filled with a white tile, meaning from the point of view of the player, the current player, whether it was mine, yours, or empty. Okay, and so this thing is taking transformer activations and asking, do those activations encode the state of the board at any given point in a sequence of tokens here that represent play? And they found that when it was evaluated on unseen test data and looking at different layers of the transformer, it was able to predict with 99% accuracy something that it hadn't been trained on, that was the board state that was generating this sequence. Okay, and then the authors also showed that they could do causal interventions based on these probe results to change the state of the board in the mind, if you will, of the transformer. So the claim was that these transformer had, by being fed sequences of text that were generated by an unseen game board and rules of the game to be able to predict the state of the world that generated this data. So that's kind of what Sutskever is claiming for language in general, that the world generates the state, language, the state that we talk about, and our talking about it allows the transformer architectures to learn a model of the world. Okay, well, the game of Othello is very different. This is a very cool result, but the game of Othello is very different from, the wide open world. So it's not totally clear that, you can make conclusions from one to the other. But some prominent people in AI were very impressed by this. This is clear evidence of a language model developing an internal world model, says Chris Olah from Anthropic, and Andrew Ng said that, do they really understand the world or just give the appearance of understanding? And he took evidence from Othello to show that these LLMs build models of the world, how the world works, which makes me more comfortable in saying they do understand. Okay, so that's one set of opinions, but others aren't so confident in this understanding interpretation. So Yann LeCun, of course, famously doesn't think LLMs understand or perform sort of the kind of reasoning that you would be able to do by understanding. He says they're more like systems that do approximate retrieval from their training data. And Rao Kambhampati of Arizona State says it even more like snarky way. He says emergent abilities, the preferred euphemism for what your LLM does when saying approximate retrieval sounds too unsexy. So these two are on the opposite side of the understanding debate than Andrew Ng and Chris Olah. So how do we evaluate understanding in large language models? We don't have the same kind of experimental sort of linear probes that can map ChatGPT's internal states to the world models. No one quite knows how to do that. But we can do sort of more behavioral experiments. Well, we can just look at their behavior, kind of give them a Turing test. And that's, I think, what most people tend to do and think that these systems understand. But of course, it's subject to the ELIZA effect, where we humans tend to project understanding onto anything that talks to us in natural language. Well, then we can do something a little more objective. We can test them on benchmarks that are meant to test understanding. So there was recently a news feature in Nature, which said AI, from April 15th, that said AI beats humans at basic tasks. Okay, and the tasks that they gave were reading comprehension, image classification, computational level mathematics, etc. And they now nearly match or exceed human performance in these tasks. And here's the plot that went with the article. This was actually adapted from the recent AI index report. So here's the human baseline on various benchmarks. And notice the names of the benchmarks: basic level reading comprehension, visual common sense reasoning, multitask language understanding. So these terms are being used to describe the benchmarks. But the problem is that these are based on specific benchmarks. And it's not always the case that even if a benchmark has the word comprehension or understanding in it, that doing well in it requires comprehension or understanding. And that's because of these kinds of shortcuts that we've seen in that I showed, like for the ruler in the skin cancer image, but there might be much more subtle ones. And there's also the question of data contamination, to what extent do these benchmarks actually, or similar questions kind of appear in the training data? So I think the problem is, you can't really say that just because a system has surpassed humans on a particular benchmark, that it really has achieved sort of the human level understanding that it takes to do the bit more general task of, say, visual reasoning. And that's sort of a fallacy that this Nature paper is just propagating. Okay, so there's been a lot of papers detailing the kinds of shortcuts that can be learned by machines in vision and language and other tasks. Okay, a very popular thing to test their understanding has been to give them standardized tests designed for humans. We've seen the headlines of ChatGPT passing business school, law school, and medical school exams. And but we have the same problem with questions of data contamination and shortcuts, and more generally, the issue of test validity, that performance on such tests might not correlate with performance in the real world in the same way it would for humans, or we would hope it would for humans if the test is valid. So it's not totally, you can't necessarily conclude that these standardized tests have shown the kinds of understanding that humans need to pass these tests. And then, so there's been a lot written on that. I won't go into that in detail. Finally, we can evaluate them on the tasks that require the correlates of understanding, that is the ability to make abstractions and to reason. Well, here's a paper that tested GPT-4 on several, tasks that involve abstraction and reasoning. And the blue lines are how well GPT-4 did on the original version of the task. The red lines show how well they do on what these people call counterfactual tasks, that are tasks that meant to test the same understanding, sort of abstract understanding, but change the content of the test so that it would be less likely to be in the training data. So just to give you an example, let's look at the code execution task. So here, GPT-4 is very good at looking at little snippets of Python code and printing out what the code would return. And here's like a prompt: you're an expert programmer, what does the following code snippet return? And you can see that GPT-4 does quite well on this. But the authors came up with this counterfactual task, which is the same task, except they say there's a new program language, Thypon, which is, an imaginary one, which is identical to Python, except that lists and arrays and so on use 1 indexing instead of 0 indexing. That a list would start with 1 instead of 0. Now, what does the snippet print? And you can see they gave it lots of different tests along these lines, and you could see that its performance dropped dramatically. And the conclusion from this paper was, while current LLMs may possess abstract task solving skills to a degree, they often also rely on narrow, non-transferable procedures for task solving. So this kind of generalization or abstract task solving that understanding permits doesn't seem to be always being used by these systems. And there was another paper called Embers of Autoregression that showed something very similar. And I'll talk a little bit about my own group's work in this area. So there was this paper from 2023 from a group of cognitive scientists at UCLA who showed that in many domains, like in 4 different sort of idealized domains, GPT-3, which is the one they tested on, was able to beat UCLA undergraduates in analogical reasoning. And this got some press, found that undergrads get beaten on questions like those that help get them into college. So Webb et al. Adopted the letter string analogy problems of Hofstadter that I myself worked on in my PhD. So questions like this: we have a string of letters that changes into another string of letters. Do the analogous change to this new string of letters? And, using notions of sequence, successorship, and predecessorship, and grouping in the alphabet. And so there's a whole variety of analogy problems that can be expressed in this idealized domain. And so what they found, and I'll just give you briefly, was here's the accuracy of GPT-3, and here's the accuracy of humans. so these humans are UCLA undergrad psychology majors. And you can see that, the best ones got all of the problems right, but this is the average. And they concluded that there are emergent abilities for analogical reasoning in LLMs. And this was only one of 4 domains, but it's the one that we looked at. So what we did, my collaborator Martha Lewis and myself, used this counterfactual task paradigm to evaluate the generality of this. Okay, and we found, we repeated the experiment, but now we also added some later GPT models. And we also repeated the human experiment using the prolific academic site rather than, psychology majors. And we found actually even on the original tasks, people in our study, people did better than these systems. So this is just a difference of population. But then we looked at the counterfactual study, which is instead of giving an alphabet in the original order, we swapped some letters. So here the letter M is swapped with the letter E. So this is sort of analogous to that Python, new version of Python. So here we're just saying, here's a new version of the alphabet, sort of counterfactual version of the alphabet. Now do this analogy problem. And you can see here that, MVGHI, well, there's a V here instead of an F, and that changes to MFGHI. What does FGLIJ change to? FGLIJ, well, it should change to FGHIJ. So we also looked at alphabets involving non-letter symbols, the same general idea. And we asked people and these GPT variants on these problems. And this here's the number of letters permuted in the alphabet. And this is the symbol alphabet. And this is the accuracy. And you can see the blue dots are humans. They are staying fairly constant across the different counterfactual tasks. And the GPT variants, this is the original task. They're doing not as good as the humans, but not terribly, but their performance goes way down with the different variations. So we concluded that these systems have not achieved general analogical reasoning abilities, at least in this domain. So the take-home message here is that large language models are better, often dramatically, on solving reasoning tasks that are similar to those seen in the training data, but not to those that are not similar. This reflects some failures of abstract understanding. So how is it that we can get machines to learn and use human-like concepts and abstractions? Well, let me give you a really short overview of how some people in cognitive science think about human concepts. We think about concepts as being mental models of categories. If you have a concept of a dog, there's a category dog, but your mental model of the dog might be, involve things that you've experienced with dogs and other more abstract notions of dogs than strict just listing of different, pictures of different dogs. And, we have mental models of whole situations and events and one's own self and your internal state. So concepts are these rich mental models. So let's consider a relational concept, the concept of something being on top of something else. We know that concepts have compositional structure, that if you understand one thing being on top of another, you can say that another thing's on top of those things and so on. If you understand a cat on top of a television, you can also understand a television on top of a cat. I got this middle picture to be drawn by DALL-E, but when I tried to get it to draw a television on top of a cat, it wasn't able to do that, at least when I tried it. Concepts have causal structure and enable predictions, reasoning, and common sense. Babies at a very early age learn about blocks that are on tops of other blocks and how you can change the state of those blocks and what happens if you push on it. Kids learn to the horror of their parents how to get their own bodies on top of things. They understand the concept so that they actually can reason about how to change their own state so that they're on top of something. And kids learn sort of the topological notion of on top of, that shoes go on top of socks in the sort of three-dimensional way, and therefore you have to put your socks on first. So just some few examples. And also concepts can be flexibly abstracted to new situations via analogy and metaphor. You know, we have all these metaphorical uses of on top of that don't involve spatial configuration. You know, I'm on top of my work, at the top of the hour, at the top of one's voice, and so on. So we're really good at this kind of metaphorical extension of concepts. Larry Barsalou, a cognitive psychologist, gave this definition of concept. It's a competence or disposition for generating infinite conceptualizations of a category. So you can see that it's a generative model. And that's, you know, you could see that with my examples of on top of. And George Lakoff and colleagues wrote extensively about how abstract concepts are actually learned via metaphors involving sort of more core primitive concepts, like social interactions being mapped onto physical temperature. She gave me a warm greeting, or status being mapped onto physical location. She's 2 rungs above me on the corporate ladder. There's also some people who have proposed the so-called simulation hypothesis, that concepts, both abstract and concrete, are grounded in mental simulations of physical situations. So Barsalou believes that. Also, people like Josh Tenenbaum have written about simulation is the way that we understand concepts and we understand the data that we encounter because we simulate, we're able to internally simulate what's going to happen and how it's going to, you know, relate. We can make predictions and do reasoning via simulation. And Spelke and others have proposed that all concept learning builds on some innate or perhaps early learned systems of core knowledge, which they propose involve things like objectness, numerosity, things like some sets are greater than other sets, some things are bigger than other things, basic geometry, topology, and agents and goal-directed behavior. So I'm going through this really fast because I want to get to this work from Cholet, which I think is really interesting. So Cholet is a researcher at Google who wrote this paper on the measure of intelligence. And he was trying to come up with a way to sort of have a benchmark or a corpus of tasks that are built on these sort of core knowledge primitives, and that require you to be able to do concept induction and abstract reasoning, and to fairly compare humans and machines on this kind of understanding task. So here's an example of a task from his corpus. The whole domain is on this grid, these 2D grids, and there's 10 different colors. And so what happens is you can give some number of demonstrations. These are like training examples where one grid transforms into another grid. And I'm here giving three demonstrations of the same abstract transformation. And now your job as a solver is to generate a new grid that applies the transformation to this test input. So you have 3 training examples, and now you have to generate something that solves the problem with respect to this test input. So it's a very small few-shot learning task. And you can probably see what's going on here, that, you know, that you have to understand what an object is in this world. You have to understand sort of spatial direction, that this thing is pointing in a certain direction. You have to understand the notion of boundaries and some other very basic spatial concepts. Here's another task from the ARC corpus. And here you have to understand sort of shape invariance. You shapes, the same shapes, the equivalence sort of class of certain kinds of shapes get colored to the same color, no matter what direction they're pointing, or no matter what orientation they're in, no matter how big they are. So Cholet came up with 1,000 tasks. This is called a task, published 800, held out 200 as a hidden test set, and then set up this competition on the Kaggle platform. So this was in 2022, I think, and people could enter programs, after looking at the 800 published tasks, they could enter programs that would be then tested on the hidden tasks. And in the end, there were like 900 teams, and the best program got about 20% accuracy on this hidden test set. Each program got 3 guesses per task. And if one of them was right, the task was considered to be solved. The ensemble of the top 2 programs was about 31% accuracy. These were program synthesis methods that tried to create a program that would do this grid transformation. Okay, and then there was another competition the following year, 2023, where you could win 1,000 Swiss francs for every percentage point above the current world record. And I think the outcome of that was somebody got up to 34%. And so that's where we are now. But there's some problems, I think, with the original tasks. I think they're a wonderful benchmark for looking at sort of understanding basic concepts. But some of them are actually too hard for humans in Cholet's corpus. And I think that's sort of why these systems are doing so poorly. But also, they don't systematically test understanding of concepts. Here I mentioned, shape invariance, but just because a program might be able to solve this doesn't mean it has a general understanding of shape invariance. You really have to test it systematically on variations of that underlying concept. So that's what our group did. We created a new benchmark that we called Concept Arc, which these are my 2 collaborators on that. And our Concept Arc benchmark is a set of concept groups, 16 of them, for each of which we created many variations that varied in complexity and degree of abstraction. But we also tried to design them to be easy for humans. And here are some of the concept groups that we looked at. So let me give you some examples. We had a total of 30 tasks per concept group with 480 tasks. So here's an example from our corpus of one of the top, above versus below, or top versus bottom. I can't remember exactly what this was, but anyway, you can see it's like remove the bottom object. That's what the transformation is. And we tested this on people on Prolific. We also tested the Kaggle winning program and GPT-4 using a text-only version of these problems where we just give sort of the cell values of each row and column of the grid. And everybody got it correct. But that doesn't mean that everybody understands the concept of top and bottom robustly. So here's another problem testing that same concept. So color the top row red. Everybody got that one right. And here's another one. This one is remove the top and bottom object. Humans 100%, but the 2 programs we looked at were incorrect on this. So they didn't have as robust an understanding. Here's another example concept. This is from looking at the concept of center. Here, the idea is to extract the center color. Okay, everybody, well, humans, 7 out of 8 humans got this correct. The Prolific platform's a little bit, it's a noisy measure of humans because some people aren't really trying. This one is extract the center object. Humans 100% got that correct. These 2 programs got it incorrect. And this was to move the colored dot to the center and extend it. Humans got that very easily, but these programs got it incorrect. And when we did a very thorough comparison on both the text-only GPT-4 and the vision version of GPT-4, when we could give it the image versions, here's what we found on these different concept groups. Basically, humans overall are doing quite well. Everybody's given 3 guesses, humans and the programs. The Kaggle first place gets about 51% overall, which is better than the 20% it got on the original ARC set, because these are easier, but still far from humans. GPT-4 with text only gets about 33%. And GPT-4V with images surprisingly only gets 15% because the image processing abilities of these, multimodal language models don't seem to be that great, to be honest. So that was a little bit surprising. But anyway, to conclude my last minute, can AI understand the world? Well, I think in principle, yes. There's no reason why an AI system in a machine in principle can't understand the world. I mean, we can debate about that if you want later on. Current AI is amazing in many ways, but it has many failures of understanding, which make it untrustworthy. And we've seen that, with many, many examples that people have shown of various tests of AI systems. And I would say that to understand the world in a human-like way, AI systems are going to need some kind of human-like core knowledge systems and the resulting concepts that I talked about that are mental models built up via composition, analogy, metaphor, and causal structure. Can AI systems achieve all this without embodiment or active interaction in the real world? That's an open question. And I think that, I would argue embodiment and active interaction are going to make it a lot more easy to gain understanding of the world, but I'm not sure whether they're never going to learn that from language and, say, images alone. So I don't know. All right, so I'll send my slides to Stephen and he can post them. And here's some citations to some of the papers that I used in making this talk. And I'll stop now and happy to chat. And I think maybe Kyle is going to do a response.
Thank you very much.
Yeah, thanks, Melanie. That was great. And as usual, always like so clear and balanced, kind of explaining everything on both sides in a really clear and sharp way. So I have some slides. Is that okay to share some slides?
Yeah, that's fine.
Okay, yeah.
Est-ce qu'il peut partager? Yes, you can share.
Great. So yeah, I was going to a bit. Let me just my Zoom thing is in the way here. Yeah, you can see these now.
Yeah.
Yeah, so I was going to do a bit of a response and also kind of while I'm at it, sneak in a bit of a Dennett tribute, in part because over the last year, I've been working with the philosopher on some questions about language models and meaning and reading a bunch of Dennett. So we kind of respond to him. And so I had some specific Dennett thoughts. I thought this would be the right venue to share. So one of the things Melanie mentioned was Eliza. So Eliza is like the kind of simple chatbot from years ago, which was basically doing very simple kinds of lookup. And I think we'd all agree it's very easy in that case to say, no, Eliza doesn't really understand because it's just doing some kind of simple lookup. And if you actually go and look up the answers and kind of understand what it's doing, that's going to give you a much better understanding of the system than positing some kind of understanding. And I think part of the reason why these the questions of do LLMs understand seems kind of more complicated is because understanding what they're doing is more complicated, right? And if you end up with an answer like, well, it's a big neural network and it's predicting the next word, well, it's kind of, now it's also doing this RLH stuff, and here's this whole literature on interpretability, blah, 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 right? It's not a very satisfying explanation of its behavior. And so I think this gets into kind of interesting questions, thinking about the intentional stance and what that might have to say about something like understanding. Right, so this is kind of Dennett's very famous idea that a system has attitudes, if like specifically often thinking about things like belief, if and only if its behavior is well explained by the hypothesis that it does. Right, so if an alien is predicting human behavior at the atomic level, even if it could, for some reason do that perfectly, the alien would still be missing something about explaining a human getting coffee or performing everyday activities. if it did in some way posit that humans have beliefs, desires, and intentions. Right? And in fact, explanations that don't have those things wouldn't be tractable. Right? And Dennett's story is that's what belief is in some deep sense. And it kind of raises the question if something like that is a way to think about understanding. So, if I have ChatGPT, here I had it generate a story. I told it to generate a story about Dan, a French professor at Harvard who works on proofs in AI. And it generated just a horrible story. I won't even read this. It's just like a kind of cheesy, corny story. But then you could ask this question of, is it fair to say in some sense that this has beliefs? And on the one hand, if a human's interacting with ChatGPT, right, and gets this output and then wants to continue the conversation, it's kind of natural and maybe even useful to say, well, it seems to think Dan's a French professor. It seems to think Dan has brown hair and uses he pronouns. It seems to maybe have some beliefs that a French professor has students and give lectures. In this example, it seems to say the professor is sipping tea, which it thinks is Proustian. So attributing these kind of beliefs might actually be helpful in predicting its behavior at some very high level. At the same time, predicting its beliefs is going to also mislead you in all kinds of ways, like assuming that it has beliefs and understanding, like all these examples Melanie showed, right? Malignancies measured with rulers, stop signs and billboards, right? All these well-tested examples in which assuming some kind of higher understanding is actually just going to end up disappointing you because the model is actually doing something which is not that richer, deeper kind of thing that humans naturally want to attribute. So I think there's a Dennett passage in the intentional stance, which I think is actually about vervet monkeys, but is kind of interesting to think about in the context of language models. And so I'll kind of read this out, which is not wanting to feed the galling stereotype of the philosopher as an armchair answerer of empirical questions. I will nevertheless succumb to the temptation to make a few predictions. So this is before these experiments have been done with vervet monkeys and kind of questions about their intentionality. It will turn out on further exploration that vervet monkeys and chimps and dolphins and all other higher non-human animals exhibit mixed and confusing symptoms of higher order intentionality. They will pass some higher order tests and fail others. They will in some regards reveal themselves to be alert to third order sophistications, while disappointing us with the failure to grasp some apparently even simpler second order points. No crisp, rigorous set of intentional hypotheses of any order will be clearly confirmed. The reason I am willing to make this prediction is not that I think I have special insight into vervet monkeys or other species, but just that I have noted as anyone can that much the same is true of us human beings. We are not ourselves unproblematic exemplars of third or fourth or fifth order intentional systems. This gets at this kind of question, I think that's come up a couple of times, the relationship between AI systems and non-human animals and how we can think about this relationship. I don't think there's an obvious answer here, but I think this passage kind of has some interesting resonances, right? This idea that in some ways they can pass some of these sophisticated tests and in other ways completely fall down on them. So maybe something to discuss. This is this paper where with the philosopher I mentioned where we get into that a bit more. And then I thought I would take 1 more minute to tell a quick Dennett story, specifically about Dennett as crossword constructor. So I'd given a talk at the Santa Fe Institute where Melanie hosted me, a talk about language models. And at the end, Dan Dennett kind of popped in on Zoom. I had no idea he was in the talk, which was kind of exciting and terrifying. And he asked this question, how language models would do on a particular kind of word game. And the word game was something like this. So I'll start by giving you a country, then give me the name of a world capital that starts with the last letter of the country. Next, give me the name of a country that starts with the last letter, and so on iteratively. And so I said, I don't know. And I followed up by email with him and showed him that, look, ChatGPT can kind of do this task. And I mentioned I had done some work on word games and language models and was also a crossword constructor in my spare time. And it reminded me when Nick Humphrey was talking about this, that he seemed quite proud to tell me that he had done this Quinean crossword. So I feel like this should be better known. This is a Dennett Quinean crossword to illustrate the indeterminacy of radical translation. And this has this really cool property that there are there's one set of clues, and there are two possible answers. And so as a crossword constructor, I can tell you this is a really, really difficult feat of crossword construction. And he did this not knowing this was the thing anyone had attempted in the crossword world. In the crossword world, it's called a Schrodinger puzzle. And it's a really nice puzzle. I solved it twice, I guess, with both solutions. And I recommend solving it. There's also a really nice kind of humanist moment here, a great human need. I won't spoil the answer or both answers, but they're both, I think, really nice and kind of fitting for Dennett. Okay, so to bring it back to Melanie and a kind of more concrete question, I wrote down a couple kind of ways that understanding came up, both in Melanie's talk and in some of the other sources she was citing. On the one hand, we can talk about do models understand? And on the other hand, often it gets couched as seem to understand in some non-trivial sense, can be said to understand the world as opposed to simply understand in some more general sense. And so I guess what I was thinking is kind of what hinges in particular on this word understand, and kind of how should we be thinking about understand versus these kind of hedged versions of understanding, or other kinds of related phenomena that we might talk about. Yeah, maybe I'll put that back to Melanie there.
Yeah, thanks. That was great. I'll just say that at another meeting I organized here at SFI on understanding, David Chalmers gave this great talk about conceptual engineering of the word understanding. And he had all these sort of prefixes like E understanding and C understanding, and, you know, just kind of a taxonomy of understanding that he felt we would have to split up the word, 26 ways to really make sense of what everybody means by it. So maybe that's the only solution.
Yeah, I mean, that's, having spoken with philosophers a bunch, I think that's I think a philosopher's answer is often to kind of break them up. Like as a linguist, my inclination is just that understanding, the meaning of understanding is how it's used kind of in the world, and it's going to be some fuzzy, vague thing. And then when you try to pin down exactly what it means to understand, you get into these like linguistic questions. So yeah, were any of his definitions like particularly salient or relevant for these questions, like for the kinds of questions that, because like I think it's probably clear, like what we most care about is like the downstream application in some sense of whether they're understanding, like what that means for all kinds of things in the world.
Yeah, no, I agree. Yeah, I mean, I can't remember all of his, I'd have to go back to his talk, but he had, I think they were quite salient. And the talk's on YouTube if anybody wants to look it up.
Yeah, and he's speaking here on Monday, I think, right?
So maybe he'll talk about the same kind of thing.
Yeah.
Let me just intervene. I'm not going to say anything about the topic. I want to say something about Kyle.
Yep.
You'll see my face in a second. Kyle, that was a spectacular discussion, and I wish it were a model for everybody else for their discussions. I think there was an unfair lead you had because Melanie sent you her stuff, and so it's my fault. I should have asked everybody to send their material to their discussant, but I think you did a terrific job, really a terrific job.
Thanks.
And if it turns out not to inspire any commentary, it's because you did too good a job. Any commentary? Either from here, I see there's some compliments. Catherine complimented you, Melanie, for your talk. And then Alina, thank you for the talk. What do you think is lacking in LLMs or AI in general for a more complete world understanding? That's a good question to ask you.
Yeah, I mean, I wish I could answer that completely. But I don't think any of us really know. And none of us have a complete world understanding, of course. So I'll just try and riff a little bit on that. What's lacking, concepts of the kind that I talked about, with all of these abilities for compositionality, for metaphor, for infinite generation of instances, and I think it's important to say that none of us have a complete understanding of the world. None of us even have like a very small understanding of the world. We understand a little bit, and different people understand different things. And one of the important things about human intelligence is our ability to call on other people in our social networks, and or to use cultural technologies to complement our understanding. And I think AI really focuses on this individual agent that's supposed to do everything, rather than some kind of more collective society-like agents. Minsky talked about the society of mind, and I think that this sort of more social, more ability to sort of go beyond one's own understanding is what really accounts for human intelligence. So that's my riff. I think Gary has a question.
Gary, you're on.
Yeah, thanks. And let me second or third the comments of that. Melanie, that was a fantastic talk, and Kyle, thanks for that really wonderful commentary. Melanie, so I wanted to ask, so kind of in response to the last question, you had a slide, can AI understand the world, where one of the points was that AI systems may need human-like core knowledge systems and resulting concepts. And I wanted to kind of get more clarity on that, because the kind of core knowledge systems that Liz Pelkey enumerated, one might say that those are the easy things to learn. That's a separate question of whether humans have those kinds of innate core knowledge systems. But for example, kind of inducing a sort of concept of object from visual experience is not a hugely difficult problem, and kind of figure ground segregation, and and for humans also, it doesn't come for free. So there's a prolonged developmental trajectory. And so I guess I'm wondering whether, things like number, causality, like arguably those kinds of things are learnable. How strongly do you feel like they have to be built in the way that Spelke proposes? And then another question is, so you said in that same bullet point, mental models built up via composition, analogy, metaphor, and causal structure. And I think there have been some demonstrations of LLMs learning this kind of stuff. LLMs are great at metaphor, interpreting metaphor, explaining, what do these things that kind of relying on the same metaphorical frame have in common. They're arguably very good at that. The gap might be that, they're not, like, these metaphors were invented by people over time. They're not invented by individual language learners who are learning it from input, but like they are the products of human culture and ingenuity. And there, I think we have much less evidence that LLMs are coming up with novel metaphorical constructions that make sense of the world in the way that natural metaphors do for people. So yeah, that's all.
Yeah, no, I think that's a good question. So on the core knowledge stuff, so I'm not, well, I'll push back a little bit that things like objectness are easy to learn. There were huge, ImageNet had a huge number of training examples, and yet the programs that were trained on ImageNet didn't learn about objects. They didn't learn how to segment. And that was, something that you had to learn and be trained on quite separately. I think that was, one of the, I remember there was like when DeepMind trained, used reinforcement learning to get one of their systems to play Atari games. and could do Atari, they could play Atari games really well, like Breakout, was really good at Breakout. But then somebody did an experiment where they moved the little paddle in Breakout a few pixels,
Yeah.
and the system just couldn't do it and the reason
Yeah.
was it hadn't learned about objects, and they had to sort of program in the notion of objects. It had just learned about pixel configurations. So I'm not sure how easy it is to learn about objects in general.
Yeah.
And we know that, like, one of the things that ChatGPT is, at least, or these vision multimodal vision systems are bad at, is counting.
Mhm.
So I don't know how easy they are to learn, or whether you have to have them built in. So that's, I think, a kind of a question that we should investigate.
Yeah. Well, so I mean, it would be kind of remarkable, right, if one could learn a stable concept of objects from static images, right? And humans don't, and one wouldn't expect them to. But yeah, I take your point that, even a young child, right, like, is more robust to this kind of, right, translation, manipulation, right? And yeah, absolutely.
Yeah, and your second point, which I'm now trying to remember, you remind me
Just
what
about metaphors.
Oh yeah, metaphors. Right.
Yeah.
Yeah, I'm not sure. Impressionistically, I would say yes. ChatGPT is really good at metaphors. It can understand metaphors really easily, but I haven't seen a study, and maybe there is one, about sort of new novel metaphors that no one's ever used before. If it can figure those out, because most metaphors are obviously in the training data. So I'd love to see that.
Yeah, I'm not aware of that study either. Yeah, I'm drawing on, like, your example of top of the world and top of one's work, right? That, and I completely take your point that, like, the human kind of concept of top is this sort of generative, causal, flexible kind of entity, right, that can accommodate all of these uses. But at least in that case, like, ChatGPT can interpret all of these phrases and variants of those phrases.
Sure.
But that's still not the same, as extending it, right?
We need the counterfactual
to a
task.
domain. Yeah.
Test.
Mhm.
So yeah.
Thanks.
We have lots of questions in the comments. Are some of the people who put up those comments brave enough to raise their hand? It'll save time. Okay, Julia, go ahead. I'm going to try to give you access right away. Second. For everybody else who wants to do it, please do it. Julia, do I have to do something else?
Hello, sorry, it takes a minute for the privileges to change. Thanks so much, both of you. That was great. I was wondering, so looking at, like, the interior layers of models, sometimes you can find really easy to interpret looking artifacts. Like, we passed a bunch of individual tokens through and saw, like, for the word bank, you can see clusters that seem to align with the senses that a human would recognize for the word. So how is it that the model can build up concepts at the word meaning level without having these lower level concepts that are necessary for people, like the ones that would enable, like, top and bottom, those tasks that you were talking about? Is it because that kind of information is different in that it can be encoded through one-dimensional relations of symbols in the language that the LLM has access to, whereas these other primitive concepts cannot be encoded that way? Or yeah.
That's an interesting question. I don't know. I think if you ask, on our tests on the little ARC problems that we gave GPT-4, I'm not sure what it wasn't. We didn't describe it in terms of language. We didn't describe the scene in terms of language. We left it as kind of a more visual task, either by giving it a text version of the grids, that just give the, different colors in the different squares, or by giving it an actual image. I think that maybe that there's a textual understanding that these systems might have that doesn't yet transfer to their more, visual understanding. And if we said something like, oh, there's we used the word top, or we kind of gave it more of a high level description of these scenes, it would be able to do much better. But of course, the whole point is to be able to abstract that from the image. So I don't know. I've been surprised, I have to say, at how much these systems are able to absorb via language about sort of the physical kinds of concepts, and it's just goes to show how expressive language turns out to be. But yeah, but what's also been surprising is sort of how far behind the language only versions the multimodal versions seem to be, at least in reasoning. Stephen, should I call on people?
Yes, please.
Okay, so there's a question from Finn.
Yeah, Finn Dobler raised his hands, but then he says he's not asking. Finn, do you want to ask a question? Well, I don't know. Bill Clancy's there. Bill, you want to ask your question out loud? Lawrence, I see. Good. We have a clear hand there. Lawrence, go ahead.
Sure. Yeah, I'm thinking about in terms of how humans understand the world and navigate the world, right? One of the ways we navigate the world is by understanding it and using our conceptual apparatus to interpret it, right? That's what we usually think about in terms of rationality. But we also know that we have a sort of a secondary system for navigating the world, and that's heuristics, right? So this is Herbert Simon and Gerge Gerenzer and that whole crew. So I'm wondering to what extent you think that the concept of heuristic might better apply to large language models than concepts and understanding and and logical application of concepts to some kind of understanding of the world.
Yeah, I mean, a heuristic, I'm trying to think about that. I'm not sure if there's that much difference between what I was calling a shortcut and a heuristic.
Sure.
So, sometimes we have heuristics which work really well most of the time, but sometimes they don't because they're heuristics. Right. They're kind of shortcuts. They're, and then when they don't work, they become called cognitive biases. And it's certainly been shown that large language models have absorbed similar cognitive biases to those humans have, which maybe isn't that surprising. That they'll use the same kind of judgment heuristics that humans use. So maybe heuristic is a good way to think about it, but I'm not exactly sure how to kind of formalize that.
Yeah. Cool. Thanks.
Friedemann has raised a hand, so I think that means he wants to ask a question. Friedemann? The trouble is that as I flick through all of these comments, sometimes they turn themselves on by themselves, and it may be unintentional. Friedemann, are you there? Sorry for this.
Do you understand me now?
Yes.
Okay, now it seemed to be impossible to get the microphone going, but now it's working. Thank you. Yeah, thanks for an excellent talk. How do you? It was amazing to see what GPT cannot do, and it's really it's really great how you demonstrated this. But what could be the solution? What kind of is there a possibility to force this kind of system towards maybe building the right representations? And is it so that one might be able to force it to build symbolic representation, as Josh Tannenbaum suggested before, that might be a critical step towards better better performance.
Yeah, I mean,
What's your solution? Is there a
yeah,
solution?
I don't know. I don't know what the solution is. Obviously, that's a big open question. But one thing that a lot of people have been doing is having the system generate code instead of language. And these systems are quite good at generating code. And often if you ask them a question, you know, give them some kind of reasoning problem in language and they try and solve it in language, they get it wrong. But if they try and write a Python code to solve it, it'll get it right. So, you know, that it's maybe so some people are trying to get to use like large language models trained on code to do the kind of program synthesis that you might need for, say, those ARC problems. That's one approach. But I don't know how general that's going to be. I'm not sure you can write code to solve all the problems that are going to come up. And it's certainly not very, well, it's arguably not human-like, you know, so I don't think that's what we're doing, but who knows? I don't think we have I don't think we have a Python code generator in our brain. But anyway, I think, you know, one thing that I would say is that we might, and this is, you know, the thing that Gary Lupian brought up, that he was sort of, I think, asking, how much do we have to build into these systems? How much is built into us? That's very controversial. How much do we have to build into these systems sort of as prior knowledge to have them be able to bootstrap sufficiently? And I think that's you know, one big question that people are grappling with. So I don't know.
Well, the alternative approach, if I may make a mini remark, the alternative approach might be to change something in the neural architecture that makes the system build representations.
Yeah.
And in our work, we have been showing that if you make the neural network more neural, more brain-like, you may that's a necessary consequence that symbolic representations emerge, or something that can be likened to symbolic representations. Anyway,
interesting. Yeah. That I like that approach. I think that, yeah.
Thank you. I liked your talk very much.
Thank you.
Okay, this is Professor, this is Sarah Robert again. As soon as I can turn my mic. There you go.
Yeah, I'd like to tell something about what happened to me last fall. Here at UQAM, I teach logic. And during my last fall term, I had two students who gave the same answers to the questionnaire. So I checked with ChatGPT, and I've seen that they have cheated because they were not allowed to use ChatGPT. And I noticed that ChatGPT they had 42% as a final grade. So ChatGPT was not very good in that course of logic. And it was a course of introduction to logic at undergraduate level. And I noticed that ChatGPT was particularly bad at solving the kind of problem that is close to what you presented in the experiments you talked about. For example, I think about a problem in which I take logical formulas written in the North American way of writing logical formulas with the symbols that we use here in North America. And I gave a class about the Polish notation. And I asked the students to translate the formulas in the Polish notation. And I think that in order to succeed that exercise, they had to abstract the formal structure of the formula and then to translate it to the Polish notation. And the translation involves analogy, to abstract the formal structure and then to analogically translate it in the Polish notation. So I want to, if possible, that you, Melanie, comment on this. I think it's quite close to the experiments you talked about in your amazing talk.
Yeah, I don't have much to say. I mean, that's another interesting example. of course, these language models are a moving target because they're always being retrained on stuff that people have prompted them on. So if you give the same test again, it's there might be some data contamination, but you know, I don't know. I mean, people have shown again and again that these systems have trouble with abstraction and generality. So I guess that's just another example.
I think I will make use of this lull to read the statement that Doug Hofstadter, Melanie's former advisor, sent about Dan Dennett, and we can take it if the people in the general audience that have raised their hands but that have not spoken up decide to get some courage, they can do it after I finish. He wrote, I just received the very sad news about the passing of Dan Dennett, a lodestar in my life and in many thoughtful people's lives. Dan was a deep thinker about what it is to be human. Quite early on, he arrived at what many would see as shocking conclusions about consciousness, essentially that it's just an emergent effect of physical interactions of tiny inanimate components. And from then on, he was a dead set opponent of dualism, the idea that there is an ethereal, non-physical elixir called consciousness over and above the physical events taking place in the enormously complex substrate of a human or animal brain, and perhaps that of a silicon network as well, executing algorithms. Dan thus totally rejected the notion of qualia, pure sensations of some such things as colors, tastes, and so forth, and his arguments against the mystique of qualia were subtle but very cogent. Dan had many adversaries in the world of philosophers, but often quite a few who shared his views. And as for myself, that's Doug Hofstadter, I was almost always aligned with them. Our only notable divergence was on the question of free will, which Dan maintained exists and is in some sense free, whereas I just agreed that will exists, but maintained that there's no freedom in it. Scott Kim joked that I believed in free won't rather than free will. It was very clever, but really the negation should apply to the free rather than to the will. Dan was also a diligent and lifelong student in the sense of studier of evolution, religion, artificial intelligence, computers in general, and even science in general. He wrote extremely important and influential books on all these topics, and his insights will endure as long as humans endure. I'm thinking of his books, and now here's a litany of his books: Brainstorms, The Intentional Stance, Elbow Room, Consciousness Explained, actually explained away, Darwin's Dangerous Idea, Evolution, Kinds of Minds, Inside Jokes. He was a terrific, this is not Doug, this is me saying, he was a terrific joke teller and creator. Breaking the Spell, From Bacteria to Bach and Back. He was also a musician, a wonderful musician, a pianist. And of course, there are other ones. And of course, his last book, I've Been Thinking, really the last book, his last book ever, which was and is a very colorful self-portrait, a lovely autobiography, vividly telling so many stories of his intercontinental life. I'm so happy that Dan has not only completed it, but was able to savor its warm reception all around the world. Among other things, that book tells us about Dan's extremely rich life, not just as a thinker, but also as a doer. Dan was a true bon vivant. If anybody has ever had a meal or a drink with him, you know what that is. And he developed many amazing skills, such as that of a house builder, which you saw in Nicholas's presentation today. A house builder, a folk dancer, and a folk dance caller, a jazz pianist, a cider maker, a sailor and carer of yachts, not the big ones owned by Russian oligarchs, but beautifully crafted sailboats, a joke teller par excellence, enthusiast for an expert in word games, a savorer of many cuisines and wines, a wood carver, a sculptor, speaker of French, and some German and Italian as well, and also grew up in, his father was working for the government, and he also grew up in Arabic countries and probably has some residual knowledge of that too. And he's an ardent and eloquent supporter of thinkers whom he admired and felt were not treated with sufficient respect by the academic world. Two of these were Doug Hofstadter and Nick Humphrey. That's my part, I added. He didn't say that. Dan was also the most devoted husband to his, but after they had Dan's approval, they were much more widely recognized. Dan was also a most devoted husband to his wife, Susan. They were married for nearly 60 years, and he was a great dad to their two children, Peter and Andrea. He entertained the kids by building all sorts of things for them, and he supported them through thick and thin. I saw them up close and really admired his ardent family spirit. Both Dan and Susan had near misses with death over the past decade or two, and on one of those occasions, his own close call, when his aorta was ruptured, he wrote a remarkable essay called, if I recall correctly, Thank Goodness. Goodness note, he wouldn't say thank God, because he was also an ardent critic of religion, which was all about how the human inventors and practitioners of modern medicine had saved his life and the lives of countless others, and that it was deeply wrong to thank God for saving anyone's life, and that what should be thanked was human goodness incarnated in the form of all those people who so deeply cared about helping their fellow humans, doctors, nurses, medical researchers. Although Dan understood why his religious friends prayed for him, he thought that such actions were profoundly misguided and that belief in divine intervention was not a healthy approach to life. Like his friends, Christopher Hitchens, Sam Harris, and Richard Dawkins, the quartet was nicknamed the Four Horsemen of the Apocalypse. Dan was a committed atheist, and unlike me, that's unlike Dan, and me for that matter. I am also an atheist. He didn't shy away from applying that word to himself with all its flavors of an aggressive anti-religion stance, and he tried to explain with great patience and subtlety what is so compelling about religion to the human mind, but what is at the same time so wrong with it. Probably Dan's two greatest heroes were Charles Darwin and the philosopher Gilbert Ryle, who was his doctoral advisor at Oxford, although he had quite a few others, including, for example, Cole Porter and J.S. Bach. Dan had many friends of many sorts in many lands all around the world. I was proud to be one of them. He and Susan loved hosting their friends in their farm in Maine, which they owned and operated for about 40 years. The end of it is told in his most recent book, his biography, which they owned and operated for, And Dan himself did much of probably most of the physical maintenance of the home and fields and trees, learning a great deal from his Maine neighbors called Bertha and Basil and Bertha. I add that because he didn't have it in here, Basil and Bertha. Dan loved Maine, and he loved calling it down east, as the Maine folks do, and he loved the jargon he picked up from the farming and from sailing, and he employed it often in his writings. I was often a bit thrown by some of the terms he dropped with such ease and naturalness, as if everybody were as familiar with farm life and the sailing life as he was. I once offhandedly called Dan a tillosopher, for the till of a boat, and he loved the epithet and even embraced it with delight in his recent autobiography. Dan was a bon vivant, as said, a very zesty fellow who loved travel and hobnobbing with brilliance whenever he could. In his later years, as he grew a little teetery, he proudly carried a wooden cane with him all around the world, and into it he chiseled words and images that represented the many places he visited and gave lectures at. Dan was a truly faithful friend to me over the 4+ decades that we knew each other. He always supported my ideas, and I'm proud that he often sought feedback from me on drafts of manuscripts while he was writing, and I often provided detailed suggestions. Seldom did I disagree with the thrust of his ideas. I usually just provided suggestions for how to phrase a sentence a tad bit more clearly, or perhaps some examples that would support his point. I'm proud that over the years I moved him closer to my position on the importance of using non-sexist language in one's speech and writing. Some of Dan's insightful essays, such as Real Patterns, which I'm almost done, which talked about what exists in the abstract new two-dimensional world of John Conway's Amazing Game of Life, and by analogy about what exists in our 3D world, were deep mind openers, as was, of course, his brilliant short story, Where Am I?, which was mentioned by Nick this morning, if you listen carefully, in the chapter on brainstorms, which led to our friendship and our intimate collaboration on the anthology, that was the book that they wrote together, The Mind's Eye, way back in 1980 and 1981. Dan appreciated me in ways that I will never forget. And he counseled me wisely and emphatically concerning romantic dilemmas during the year I was on sabbatical in the Boston area. I can testify to that. There was a time when he told me not to consider someone as a potential partner because Doug was interested in her and he needed her more. He was deeply considerate and compassionate, and as I say, filled to the brim with zest and enthusiasm. He was a great dad and a great husband and a great friend, as well as a great intellectual and a great writer. He was bigger than life, as my friend David Polachansky described him one time when we were together with guests at Sam's and Susan and Dan's farm in the early 80s. I personally will deeply miss Dan, and so will so many other thoughtful people. Even people with whom Dan seriously disagreed, such as my old doctoral student, Dave Chalmers, who'll be here soon, whose ideas on consciousness are diametrically opposed to Dan, but their friendship and warm because they both valued honest human contact and respect and clear communication far above such goals as fame or power or status. Dan Bennett was a mensch, and his ideas on so many subjects will leave a lasting impact on the world, and his human presence has had a profound impact on those of us who were lucky enough to know him well and to count him as a friend. Requiescat in pacem, Dan. Yours, Doug. Now, we are at 4:56. We have 4 more minutes if there are any brave spirits. If not, I will now announce this day finished. Our first speaker tomorrow will be Kyle Mould, who gave that wonderful discussion today. Bye-bye.